Checkpoint is a mandatory process. To understand this, let's discuss blocks. PostgreSQL always reads and writes data in blocks. Consider the employee table. It has just one record. The data in this record should add up to a few bytes. We have the value 1 in the column ID and the value Smith in the column last name. However, this table will consume 8 kilobytes in the disk because PostgreSQL works with 8 kilobits blocks. A block is also referred to as a page. It is easy to verify that PostgreSQL uses blocks. For the following example, we should ensure that our table has just one record as follows. First, we create a table employee with an ID of type serial and the last name of type varchar. Then we insert a row into this table Then we find the file name and now we can check the size of the file. (8,192 bytes is equal to 8 kilobytes. So, a table with just one row takes up 8 kilobytes. Once a user makes changes to the data, those changes have been made available in the buffer, and therefore the buffer is now dirty. As mentioned earlier, the fact that a user has committed a change, it does not mean that the changes have been written to the data files. It's the job of the checkpointer process to write the changes to the data files. When a checkpointer happens, all dirty or modified files are written to the table and to the index files. The process also marks the pages as clean. It also marks the write-ahead log as applied up to this point. Checkpoints are points in the sequence of transactions at which it is guaranteed that the heap and the index files have been updated with all the information written before this checkpoint. At checkpoint time, all dirty pages are flashed to disk and special checkpoint record, also known as the redo record, is written to the log file. Until now, change records have only been written to the write-ahead log files. In the event of a crash, the crash recovery procedure looks at the latest checkpoint record to determine the point in the log from which it should start the redo operation. Any changes made to the data files before this point are guaranteed to be already on the disk. As a result, after a checkpoint, log segments preceding the one containing the redo record are no longer needed and can be recycled or removed. Now, the question is, when does the checkpoint happen? To some extent, we decide this. There are a few parameters that decide when a checkpoint should happen: checkpoint flash after, checkpoint timeout, and checkpoint completion target. The first one is checkpoint flash after, with a default value of 0 pages. Once the specified number of pages have been filled, a checkpoint occurs. The second parameter, checkpoint timeout, is a timeout value which can be set in seconds, 300 by default, minutes, or an hour. A checkpoint will occur when either the checkpoint timeout period has elapsed or the checkpoint flash after number of pages have been filled. Let's consider a server with around 16 gigs of shared buffer. This is a server that has a significant load. If a considerable proportion of this load consists in writes, then most of these 16 gigs of buffer can become dirty in a few minutes. A low setting for checkpoint flash will result in the available segments getting filled quickly and infrequent checkpoints. Similarly, a low setting for checkpoint timeout will also result in frequent checkpoints. This results in significant disk throughput. On the other hand, if we keep this value very high, this will result in infrequent checkpoints. In a heavy write system, this can result in I/O spikes during checkpoints, which affects the performance of other queries. Another parameter, checkpoint completion target, can be tweaked to ameliorate this to some extent. These parameters tell Postgres how quickly it must try to finish the checkpoint process in each iteration. With a default value of 0.5, Postgres can be expected to complete each checkpoint in about half the time before the next checkpoint starts. When we increase this value to say 0.9, the writes resulting from the checkpoint get spread over a longer period, so the I/O spikes get flattened out. One issue with very infrequent checkpoints and a lot of dirty buffer is that the time to recover might go up. In the case of a database restart, for example a crash, it finds out the last checkpoint information. It will then replay all the transactions that happen after the last checkpoint and until the last commit. The transaction or changes are read from the wall. If the volume of dirty data was huge when the system went down, this means a large number of transactions has to be replayed before the database is open for business. This implies a higher downtime. From this angle too, it is better to have more frequent checkpoints. The time to recover might be as high as the checkpoint timeout value.